Welcome, folks, to the first presentation in our series of lab exercises for our freshwater ecology techniques course. This is primarily a lab and field course focused on learning techniques for studying freshwater systems. We'll be working in teams on projects and working indoors during the cold weather unless we get ice on a lake. And then later on in the spring, we'll be working on a project on a local pond. So today we want to look at some background on waters, watersheds, and properties of water so you can understand why we're going to be doing the laboratory exercise on temperature and density in lab. So let's take a look at some principles here. So when we look at water, we have to think about how does it get to the lake or stream or pond that we're studying. So you need to understand a little bit about watershed interactions in the atmosphere. Water will be coming into the pond or lake or stream through a series of processes and moving through different zones that you need to be familiar with. And so most of the water that you see will get to a river or a lake or a pond by precipitation. And notice a lot of these processes words ends in the TION. So a lot of these are process words. It could be rain, it could be fog, it could be snow, but when it melts, it will either infiltrate the soil and work its way into the groundwater, or it will run off as surface runoff or overland flow into a lake or stream. Once it's in a lake or stream, depending upon the temperature of the pond and the air temperature above it, the water can change states and evaporate and go back to the atmosphere. Or it can be taken up through the soil by roots of plants or trees and released through leaves or needles through the process of evapotranspiration. But some of that water will infiltrate and enter geological layers below that and saturate that area and become part of the groundwater. Some of it may be moving depending upon the slope of the water table and move into a body of water that comes above the groundwater layer surface. Or you have water trapped below that in layers that's not moving. And so you can have confined aquifers, or an impermeable layer where water can't go, or a confined aquifer where water got to it but you can't get out. And so all of this is the saturated zone. Above that is the unsaturated zone where the water infiltrates through. So here's a diagram of some zones and a standing body of water, typically a lake, some terms that you should be familiar with when we look at cross sections of lakes. And so the top of the water will come to the edge of the lake shore and expand out, and then you have different zones of the lake depending upon what's happening with plants, what's happening with sunlight, what's happening with temperature, layering effect, and what's happening with the bottom. And so the open water layer beyond where aquatic plants are rooted and coming to the surface or submerged under the bottom, beyond that is the pelagic zone. And so that open water zone can be divided into three particular zones. One is the epilimnion, another one is the metalimnion, and the bottom one is the hypolimnion. And so the epilimnion is considered to be the area that's going to be involved in the photic zone. Photic zone is where you have enough light penetration through the surface where phytoplankton and floating plants can conduct enough photosynthesis where the oxygen produced equals or exceeds the oxygen consumed. And that point where it's 1-to-1 is called the compensation point for photosynthesis. Below that, oxygen lost through decomposition and respiration is greater than any oxygen that's being produced. And so this is considered to be the aphotic zone, where you really wind up with more respiration than you do production. So the metalimnion and the hypolimnion together are called the profundal zone. Now, along the bottom, when you get to the bottom substrate, organisms that are living on the bottom, muds and sediments, they're called benthic organisms or benthic invertebrates. And so that zone is called the benthos, and then below that are the sediments below the benthos. And then this area near the lake shore where you have aquatic plants, macrophytes that are rooted in the bottom, either submerged or growing up through the water surface right up to the edge of the lake. That's called the littoral zone. The key molecule we're concerned about in this course is the water molecule. And so you learn from chemistry that water is a polar covalent molecule. It is held together with unique hydrogen bonds, hydrogen bonding, as you learned in Bio 121. Why is water polar? Well, when you look at the structure of this molecule, you will see that it's a tetrahedral arrangement, and that molecules of water bond to each other because of what's happening in each molecule. So here's oxygen and 2 hydrogens. Now, because of the way the electrons are shared by this molecule, we wind up having the electrons spending more of the time on the oxygen than it does on these 2 hydrogens. And so the hydrogen's electron is spending more time over here because the oxygen needs electrons. And so as a result, because the electrons spend more time here, this end of the molecule has a negative charge, this end of the molecule has a positive charge. And so when you get another water molecule next to it, the positive end of this water molecule here is attracted to the negative end of this water molecule here. And so you'll see a lot of this bonding between the hydrogen of one water molecule and the oxygen of another water molecule. And that particular property, hydrogen bonding, is responsible for several unique physical properties of water. So this is an important graph showing the temperature, density, salinity relationships for water. And if you describe these 2 relationships, first you have to look at this graph here, showing the relationship between temperature and the density of water. And so if you look at this, it's not linear. Here at 0, the water is a little less dense than here, which is about 4 degrees centigrade. And then as it warms up, it continues to get less dense. That's an important property for us to understand for our lab and when we study lakes. Then within this graph, they've put in another graph showing the relationship for the change in density for every degree centigrade decrease at specific temperatures. And so there is about a 35 times 10 to the 5th change in density for water when it was at 35 degrees and drops 1 degree. And so notice that as the water gets colder, there's less of a change in density for every degree lowering, until you get to 4, which has barely any change in the density once you get to 4. And then as you get colder than 4, you get a little more of an increase in the decrease in density as it gets colder, which this inside of the curve kind of mirrors this curve up here. Also notice that the salinity influences the density of water as well. And so when you have, this is parts per thousand, we have a little 0 per double zero over here. This indicates salt content in parts per thousand. And so if we look at water with a 0 parts per thousand content, the density is about 1. But as the salinity goes up, the density gets greater. And we have to remember that when we study waters that could be impacted by salt. So this is a closer look at the temperature-density relationship of water, because later on we're going to study the specific heat of water. And so we're going to define the specific heat as the amount of heat or heat energy that is going to take to raise 1 gram of water by 1 degree centigrade. When we look at the temperature-density relationship, you can see water is most dense here at 4 degrees centigrade. And on this side of it, when it gets cooler, the density decreases this way. And then as it gets warmer on this side of the relationship over here, the density continues to decrease as well. So most dense at 4, and then least dense on either side of that, and especially as the water gets even warmer than 8 degrees centigrade, it gets even less dense. So here's some important properties of water to get you ready for a little practice problem that I'm going to assign for you to do on your discussion forum on the Blackboard course site. You need to know about the density of water. You need to know about the specific heat of water, which is 1 calorie per gram, 1 degree centigrade. So if you're going to raise the temperature of water that's not freezing, you need 1 calorie per gram of water to raise it 1 degree centigrade. You know water has unique solvent properties. We're going to learn about the absorptive radiation capacities of water, how it differs with wavelengths. The surface tension capacity of water is related to hydrogen bonding, and the viscosity of water that changes with temperature. But for the practice problem, you want to also know that the heat of vaporization of water, or the amount of heat it takes to change 1 gram of water at 100 degrees centigrade into a vapor, is 539.55 calories per gram. A lot more than it takes to raise it 1 degree centigrade when it's liquid. And then, for us in New England and Arctic climates or temperate climates, the latent heat of fusion of water, that's 79.67 calories per gram at 0 degrees centigrade. In other words, when you cool water down to 0 degrees centigrade and it's still liquid, it still has to lose 79.67 calories before it'll turn into a solid. Okay, so here's a little practice problem for you. I want you to do. You got a 5-gallon aquarium. It's full of water at 20 degrees centigrade. You can assume that water is 1 gram is equal to 1 cc of water. And you can assume that a gallon is equal to 3.75 liters, because you'll need to do some conversions. And you'll use the conversion of 1 liter equal to 1,000 cubic centimeters, or cc's. So you have to figure out how many calories must this aquarium lose, 5 gallons of water, that's at 20 degrees centigrade. How many calories must it lose? And the key here is to completely freeze. So I've got an example table for you on the next page you can use as a way to post your calculations and post them on the discussion board on Blackboard for thermal properties of a lake. So got to use your conversions, and you got to use those unique specific properties of water to figure out how many calories are involved total. So you got to figure out your volume in gallons. You're going to have to change that to liters, and you'll have to change it to grams. And you got to figure out how many calories it's going to take to get it to zero as a liquid. And then you got to figure out how many calories it's going to take to get all of that to ice. And if we're lucky and lakes get cold enough, maybe we'll be out there doing some temperature density profiles on a lake by using an ice auger and drilling a hole through the ice. So this is some background for you to get ready for your first lab. Hope this was helpful. Thanks a lot.